Comment. Um, just FYI, my expectations for the homework are maybe a little different than other classes. The problems are going to be probably harder than you get from whatever the standard algorithms class or something, and that's totally fine by me. They're meant to challenge you. So if you find them more challenging than your other classes, don't feel bad. That's the point. Okay, so uh, uh, and that's also why we have all these kind of leniency things and late policy and blah blah blah. Um, with the understanding that these aren't supposed to all be like very straightforward or anything like that. Okay, and if you have questions, talk to your classmates and or come ask for hints in office hours. And sometimes, as I help individual students, I think of hints that eventually I turn into footnotes on the homework as well, and try to get that out to the rest of the class. Okay, so just keep that in mind that I don't expect perfection at all, as you can already see in the lectures, right? So that's not the point. And the point is to challenge you, make you think, so on and so forth. Okay, so today's lecture, I think is a really fun one. It's called Random Sums and Graphs. As usual, let me rewind you through our wonderful journey so far. Lecture one was really about linear expectation, quick set, SAT and sorting and stuff like that. Lecture two was the wonderful heavy hitters problem. So we got to use hash functions for the first time. We really used Markov's inequality for the first time. The third lecture was more kind of hardcore hash table type of lecture. In particular, we studied this very sophisticated linear probing based approach. I'm trying to not say so much. Since I record the videos, I have become very aware of my ums. And then last lecture we did randomized minimum cut, which is pretty fun. We studied this really cute algorithm where you just randomly contract edges and actually has a polynomial chance of outputting the minimum cut. And then we found that rather than just kind of retrying the algorithm again and again from the beginning, we can do something more clever, inspired by these Galton-Watson trees, where we run the algorithm for a little while, and then we save it, we make 2 copies and recurse, and that amplification turned out to give some winnings in terms of the overall algorithm time. We also analyze this Galton-Watson process at the end of class. Okay, today, all right, so today, in terms of techniques, I'm going to introduce what's called the multiplicative turnoff bound, which we'll use like again and again and again. We'll get very used to it. For the sake of analyzing, it's not going to be so much an algorithm but it will still be an interesting result. We're going to be analyzing random graphs and certain characteristics of them. In particular, we're going to focus on something called the giant component, the existence of a large connected component. Okay, so let's start with the new technical tool. Okay, so let me. Oh man, I screwed this up. Okay. Oh, that's why. Okay, so let me ask you guys a question. Suppose I flipped 100 coins and 50 of them came up heads. Okay, should you be surprised? You're not allowed to answer questions as why not, or really anything all too existential in an academic environment. Once you start asking that about the homework, then it's all over. I'll never motivate you. Once you start asking why not about the grades, why not about your degree, why not about lunch, dinner, and breakfast. Okay, you get 50 heads, should you be surprised? Who's surprised? 5 of you are surprised. Who's not surprised? Wow, that's mostly the rest of the class except for 5, so good job. Great. Okay. Why were you not surprised, most of the class?
It's NCR 100 times divided by 2 to the 100. I suppose it's around 0.8.
Okay. Most people would say that they weren't surprised because the average is 50. Right? Okay. Now, but maybe you should be a little bit surprised because actually getting exactly 50, there's an 8% chance, which actually coincides with what you said. Okay, fine. So that's one question. All right. Now I say we flipped 100 coins and we got 0 heads. Should you be surprised? All right, you should be very surprised. What are the odds of this happening? Okay, right. Okay, so we all know this. Let me give another one. You flip 100 coins, and at most 25 comes up heads. Okay, so less than equal to 25. So there can be 0, 1, 2, 3, 21, 22, 23, 24, 25. It can be any of those. Should you be surprised? Okay, so who's surprised? Okay, I'd say that's like almost everyone. Anyone not surprised? A few people. Okay. So I guess maybe there's two things in the balance here. On the one hand, you know that the average is 50, and you're thinking that, okay, it should probably be close to 50 or something like that, and 25 is kind of far away from 50. Okay. But the flip side is that I'm giving you like 25 or 26 possibilities. It can be 25 or 24 or 23 or 22 or 21 or 20, or all the way down to 0. Right? So on one hand, it is true that, of course, we're looking at the weaker end of the range. On the other hand, I'm giving you a big range. Okay. Does anyone want to change their answer? No. Why would you? Okay. So I guess the probability, I think this is not a percent, I think this is just as a fraction, is, I don't know how I found this on the internet. I guess 2.8 times 10 to the negative 7. So the odds of getting 25 or less out of 100 coin tosses is actually quite low, even though it represents 1/4 of the total range of outcomes. Okay.
Actually, I think the main point here is that given a normal distribution of the coin toss, it is balanced, and if the cases that is less than or equal to 25 is still occupies a very small area of the whole distribution.
Right. Yes, it's saying that it occupies exactly a 2.818 times 10 to the negative 7 fraction of the distribution. All right, let me give a couple more. You flip 10 coins, and most 4 of them come up heads. Should you be surprised? Who's surprised? No one. Who's not surprised? Okay, one person didn't vote. Shame on you. Okay, the odds of that happening is 37.7, which is actually not far from 40%. Okay. Let me add a digit or two. You flip 1,000 coins, and at most 40% of them come up heads, or less than or equal to 40% of them come up heads. Who's surprised?
I will be more surprised with the 50%.
Yes. And who's not surprised? Okay, so this was the most controversial then of the questions we have so far. Okay, so these odds come out to apparently, I thought 1.36 times like 10 to the negative 10. Okay, so that seems like a small number. Okay. So if I put these side by side, in both cases, it was 40% mark. And the only difference was that I'm flipping 100 times as many coins. Okay. So what this tells you is that when it comes to this kind of concentration phenomena that we're about to formalize, scale matters. Okay. So what we're really interested in is the concentration of phenomena of many individual independent parts. Okay. We study in computer science, and when n is large, we rarely care about 10 coin tosses in algorithm. We care about a very large n. Okay. And we want to understand, or part of the theme today, the theme today is about how when n gets very large, and in some sense, there's actually more randomization out there, right? there's 1,000 coins as opposed to 10 coins. It's arguably more random. Okay. However, it's actually much better behaved, right? This is telling you that it's going to be within the 10% band with much higher probability with fewer coin tosses. Okay. So that's sort of the very interesting phenomena that we'll study, concentration phenomena. This idea that with randomization and you have n random independent parts, when n gets bigger, things become more and more predictable, even though it would seem to be more random in some sense of the word. Okay. All right. So here then is maybe a more formal thing. All right. So let's let x1 through xn be bounded random variables. The main characteristics are that they're non-negative and they're bounded above by a constant. So I put them between 0 and 1 for simplicity. Okay. And let's let mu denote the expectation or mean. I guess that's why they use mu. Okay. And the high level question we're interested in is, what is the probability that the sum of these independent random variables is very close to mu? Okay. And I'm interested today in the question in multiplicative terms. So what are the odds it's within 5% of mu, 10% of mu, as opposed to mu plus or minus 1? Okay. I'm interested in relative approximations. That's often the case in computer science because that's really the scale-free or the scale invariant version of this statement. Okay. And the high-level answer to this question, it'll be more technically specified in a moment, is that the probability of deviating from the average, so the probability of error, is exponentially small in the average. Okay. So this will be, we'll sharpen this with a real inequality in a moment, but just looking at this, it's already quite interesting. The assumptions on the xi's aren't too strong. I mean, I don't really know how they're distributed. They could be heads or tails coin tosses. They could be other random variables between 0 and 1. I'm only assuming that they're independent of one another. Okay? And it's saying that insofar as the average is very big, I'm going to be very close to the average with exceedingly high probability. Okay? So at a high level, when you have many small parts adding up to something really big, that really big average is going to be very concentrated. Okay? At some level, you have all these individual parts, they add up to get to this big target, and you need somehow them to really be off. You sort of need them to be synchronized and gang up and all, show up 0 together and stuff like that. But they're independent, so that's hard for them to do. That's sort of some intuition. All right, so let me give then the drier version of the statement. Okay, so what's actually called the multiplicative Chernoff bound? So same x, same mu as before. I've introduced another parameter epsilon between 0 and 1. This is sort of that multiplicative error that I'm allowing. So epsilon equal to 0.1 would be like 10% error. Okay. The first statement says, okay, the probability that I'm at least 1 plus epsilon times the average. So I'm too big, I'm above the average by at least an epsilon multiplicative factor, is at most e to the negative epsilon squared mu over 3. So think of epsilon as maybe a fixed constant, independent of mu in particular. As mu gets bigger, this is dropping down exponentially fast. Okay. I can't overemphasize the importance that it's going down exponentially fast. And then we have the other inequality, which is the other direction. What are the odds of the sum being much smaller than the average? Which again is going down exponentially fast in the average. All right, so that's the statement. It's incredibly useful. It's going to show up in like every lecture from now on. I'll prove it at the end if the time permits for it. Otherwise, I'll do it in another lecture, or I'll throw it in the homework or something. You'll want to know the proof. It's important. But today I want to focus on the implications and getting a feel for it and understanding some of the consequences of this statement. Okay, I want to motivate the proof. All right, any questions about this statement, just as a mathematical? Yeah. Yeah, these are actually slightly different constants, 2 and 3. Just for technical reasons, yeah. And in fact, you can come up with more complicated, slightly stronger right-hand sides as well. But of course, the more complicated you leave it, the harder it is to apply in a generic situation. The constant really won't matter for us because whatever, we'll just do big O log n or something, right? And usually a different constant here is only going to give us like a constant change in running time or something that usually we're not too worried about. It's not too big a deal. The main thing is that it's exponentially decreasing in mu. The second thing would probably be the epsilon squared dependency. Okay. All right. So my goal is to put that bound in our back pocket and study some interesting phenomena where the multiplicative turn-off bound comes into play. So the multiplicative turn-off bound we study is really about sums, which might seem kind of boring. We're just adding things up. So here we're going to study a combinatorial structure and sort of witness something similar, a concentration phenomena of combinatorial structures that is going to take advantage or use the multiplicative turn-off bound, which is just about sums in a clever way in the proof. Okay. So we're going to study a random graph. Okay, this is called the Erdos-Runny graph model. It's a big topic in some parts of mathematics and combinatorial optimization. In general, studying randomized combinatorial objects is a broad field. But the model is very simple. We have n vertices. Think of n as being very, very large as you want. And between any pair of vertices, I'm going to randomly sample an edge with a fixed probability p. From Wikipedia, this is a picture of a random graph, but it's really hard to tell if it was random once it was made. Okay, so in this model, the high-level question is, what does such a graph look like? Okay? Or does it look like anything in particular? Is it just complete noise, or maybe is there some reliable structure that emerges? And we are actually going to study the second question in terms of are there maybe certain interesting properties that a graph like this consistently has? So questions we won't study but fall under this category include like, oh, does this graph have a large independent set? Oh, does this graph have large clicks? Oh, does this graph have sparse cuts or this or that? Okay, and depending on different values of p, you're going to get different performance or different results. So our discussion is going to be about connectivity. Okay? And how big are the connected components of this graph? Okay. So here's the theorem that we're going to prove. There's some subtlety to it. Okay. So we're going to be studying random graphs where the average degree is very close to 1. Okay. So we're going to study where p is equal to maybe 1 plus epsilon over n, or a small epsilon. So if p is 1 plus epsilon over n, the average degree will be 1 plus epsilon. And it will also, we probably won't have time for it, but there's also another study of what happens when the degree is slightly smaller than 1. 1 minus epsilon over n would be the value of p for a fixed epsilon. Okay. So these are very sparse graphs. you would expect the vertex to have only one neighbor. Okay. All right. So as long as that average degree is any constant bigger than 1, with very high probability, we're going to prove that there's a connected component with a constant fraction of vertices, a huge connected component. Okay, average degree of anything bigger than 1, 1.00001, a really sparse graph. Average degree is very close to 1. We'll still have a connected component, with just a ton of vertices. In fact, if you wanted to work harder, you can actually bring this from a constant fraction of n to something much closer to n, but it just makes the analysis bigger. Okay. And meanwhile, all the other components are very small. Okay. So there's one unique, gigantic component with very high probability, and everything else is small. Okay. And what makes this extra interesting is that when we look at the case where the average degree is less than 1, so 0.999999, then with high probability, there is no giant component, and all the components are small. Okay. So somehow, when you go from average degree 0.999999 to average degree 1.000001, you get completely different behavior in the graph. Okay. Just as a tiny, tiny amount, and the characteristic of the graph completely changes. Okay, so sometimes this is called a phase transition, right? Because on one hand, sort of the input changes by a tiny amount and the output completely changes. Okay, so this is, of course, a nice model for us to study. It makes for a good class discussion, but it's not the only phenomenon in the world that has a phase transition like this. You guys have many in your own life. Does anyone want to point out some, phase transitions? Sure, ask a question. If C is equal to 1, then good question. Though people do think about this. And I should also mention that for simplicity, I just C bigger than 1 and C less than 1. But a more intense analysis will look at C is equal to like 1 plus log n over n or something. So things that even approach 1 over time, and they can still get pretty strong bounds. But it's more complicated. If C is equal to 1, I don't have a satisfactory answer at the top of my head. But I think we can do a Wikipedia search and see what it says, because people do care about this. Okay. People do care. Okay. All right, but let me go back to this other question. A high-level question about phase transitions and threshold phenomena. Anyone want to point out anything else in the world that behaves like this? Ice. Yeah. So when water goes down to 0 degrees Celsius, I guess, and whatever it is in Fahrenheit, it really turns very rapidly to ice. And when ice goes above 0, it turns very rapidly to water. Same with water going to gas and gas to water. It's not like half of it is below 0 and half of it is above 0. So that's one. Yeah. Oh, black holes? I think that's a different phenomenon, but I don't totally know. I guess black holes is always a great answer to any question. Okay, well, what about one that's very relevant for the last 3 years? Some of you are even wearing masks. So epidemics, right? So epidemiologists study models. They'll study more complicated models with more nuances and bells and whistles, okay? But at a high level, I'm not claiming to be an expert on this, but this is one reason why there's just so much emphasis on making slight improvements and trying to be a little bit safer, because small they have, there's some sort of coefficient for the average number of other people that a sick person is expected to infect, and small changes in this number, in their models make huge differences in the outcome. So that's one reason for all the sensitivity and the concern and stuff like that. Of course, the real world is complicated as well, and I'm not really an expert, but this is part of the idea. Um, other things include things like forest fires. So there's lots of little forest fires all the time, but every once in a while they become ginormous. Okay, that also has this sort of like kind of infection feel to it. And, yeah. So there's lots of nice, interesting, lots of things in physics, things to do with magnets, stuff like that. This is a pretty common uh, thing in physics. Okay, but we're lazy. We're just talking about connected components, so we don't have to worry about messy real world details. Okay, all right. So does the statement make sense of what we're going to prove? Okay, so we're going to focus on the upper bound today. C is greater than 1. I think I'll be able to point out what you would do for C less than 1. It's only a brief thing. Okay. But the proof is going to proceed in 3 parts. So the first part, and the part that's going to take us most of our discussion, is the existence of a certain gap. So okay, we're looking at the regime where the probability is greater than 1. So I'll say it's 1 plus epsilon over n for a fixed epsilon. Then with high probability, every connected component in the graph will have size either at most some log n over epsilon squared or so log n for fixed epsilon, or size at least an epsilon times n. Okay. So there's nothing in the middle. That's the claim. There's only tiny and giant components. Nothing in the middle.
High probability defined.
It was probably 1 over n squared, 1 over n cubed, something polynomially small in n. Yeah, you'll see that we can just tweak the constants in those statements and get a better exponent on their probability. Okay. All right, so that we're going to show there's no middle size components. Then we're going to show that there's at least one large component. And then lastly, and this will be the easiest, we'll show that the large component is unique. Okay, 3 parts. Most of the work and most of the kind of the most technically interesting part and why I chose a lecture comes in part 1. All right, we're making good time. Okay, so here's how we're going to set it up. We're just going to analyze one vertex V at a time and try to understand the size of the connected component of this particular vertex V. Okay. And to analyze the connected component and the size of the connected component, we're going to imagine running a search algorithm, something like breadth first search or depth first search. Okay, where sort of, I'm at a vertex, there's all these random edges, I don't know the outcome yet, and I'll kind of run breadth first search and I'll find out which of the edges are available. And then maybe I'll find another vertex, find out which edges are available, and stuff like that. There's going to be sort of an algorithmic flavor in the proof. We're not really analyzing an algorithm, but in some sense we are. Okay, so that's right. So, okay, so for a particular V, I want to understand the connected component of V. All right, so let me be careful about how I'm going to set up the search algorithm because the analysis is a little bit subtle, so it's good to do this correctly. All right, so here's what we'll analyze. So I'm going to be very careful throughout the algorithm of which at some level the edges are unknown, or I imagine I haven't flipped the coin yet until I check that edge. Okay. So I want to be very distinct about which vertices do I already know are in the connected component of V, and which vertices has my search algorithm kind of already explored and marked. Okay. So B is always a subset of A. Initially, all I know is that V is its own component. I haven't checked any of its edges yet. And B is empty. I haven't really explored any vertices. So exploring a vertex will be also checking all of its incident edges. So the way we'll set it up is saying, okay, while there's a vertex V that I know is in a connected component of V, but I haven't explored its edges yet. So the first VI would be V itself. Okay. Then I'll check all of its edges. And these vertices I know are now in the same connected component as V. So I'll add them all to A. Okay. And then now I've explored V, so V is added to B. Okay. Then I'll pick out another vertex from my set A of vertices that I know are connected to V, but otherwise I haven't explored yet. See if we find some more neighbors. I guess the average degree is 1, so it's unlikely to get 3, nonetheless. Try to find some more neighbors, add them to A, and then, okay, now I've checked V1. So V1 is added to B. Okay. So it's really no different than BFS or DFS stuff like that. It's really for the sake of the proof that I want to be very careful anytime which ones I kind of already know are connected to V and which ones I've yet to explore and stuff like that. Okay, so this is what I want to analyze. And I want to take this and just add a little bit of notation, again, for the sake of analysis. So I've taken what we just discussed, and I've just added a subscript I to keep track of which iteration we're on. So A sub I is the vertices known to be connected to V after I iterations. So A sub 0 is just going to be V, because there's no iterations yet. I only know that V is in the same component as V. BI will be the vertices that are explored after I iterations and stuff like that. And down here, I've just added the appropriate subscripts. Okay, nothing different. Okay. So in analyzing this, okay, so the next part of our analysis is we're going to try to do something clever to try to simplify our algorithm a little bit. Okay, or we're going to come up with sort of an equivalent randomized process. And in particular, we're going to work to try to get rid of B. I'll explain what I mean. Okay. So the first observation is sort of has to do with when the algorithm terminates. Okay, so the algorithm terminates once I've explored all the vertices that I know are connected, when A sub I is equal to B sub I. Okay. Now, A sub I is always a superset of B sub I. I mean, B sub I is always a subset of AI. So this is also like saying, keep going until the two sets have the same size. The size of AI is equal to the size of BI. That also means the sets themselves are the same. Fine. Now, how big is BI? How many vertices are in BI for a particular iteration I? Always I. Okay. So that means the algorithm terminates precisely when A sub I is equal, the number of vertices in A sub I is equal to I. After 10 iterations, I've concluded there are 10 vertices connected to V. So that is observation 1. The algorithm terminates if and only if the number of vertices in AI is equal to I. Okay. Not saying too much, but analytically we're kind of trying to get rid of BI to simplify the number of moving parts. Okay, Observation number 2. Okay, so let's think of it this way. So for observation number 2, okay, I've already written it out. All right, so let's say that I have AI, right? And I guess I'm searching VI plus 1. I'm in that next iteration. And that'll hopefully get me some enlarged A sub I plus 1. Okay, so how might I describe? So in our minds, I think of A sub I plus 1 as, oh, there was this randomly generated, I mean, there's a story in our head. There's a randomly generated graph, and now I'm finding out which edges are connected to VI, but weren't already in A sub I. Okay. But if I were to take that story away, I mean, what is maybe an alternative way to describe A sub I plus 1, or rather A sub I plus 1 minus A sub I, the vertices that are added in the next iteration? It might be too vague a question. Let's look at a particular vertex here. What are the odds that this vertex is going to be in A sub I plus 1? P. Because the probability of this edge is P. Okay, good. So that's that vertex. What about that vertex? Also P. Okay. What about that vertex? Okay. So all the vertices are added to become part of A sub I plus 1 with probability P. Okay, so I can think of this part of the Venn diagram, A sub I plus 1 minus A sub I, as a random sample of all the other vertices. Each of them sampled with probability P. Okay. What's great about that description of A sub I plus 1 minus A sub I is that, in contrast to the random graph story, it had nothing to do with VI plus 1. I could have chosen a different VI plus 1, and it's the exact same sample. Right? Because of this. The way the model is, all the edges are uniform. So that's observation 2. I can think of the successive A sub I plus 1, as taking the previous A sub I and adding a random sample where all the other vertices are sampled independently with probability P. All right, so what does that give us? All right, so with these two observations, so here is sort of our original running some kind of breadth first search looking thing on a given random graph. Okay, but here is kind of a different description of a randomized process, which produces the same set A sub I. So we're starting from A sub I just containing the original, A sub 1 or A sub 0 containing the original vertex. And until I reach A sub I equals I, which is the same as our terminating condition, A sub I is equal to B sub I, I'll repeatedly sample all the other excluded vertices with probability P, and whatever I sample I add to the set, and then double check the cardinality and repeat. Okay, so this will give you the same distribution of A sub I's. Okay. But the advantage is that this version simply has less moving parts. We've kind of gotten rid of the V's, we've gotten rid of the B's. I'm just looking at a set where each iteration I'm randomly growing it, randomly growing it, randomly growing it, and hoping that after 10 iterations I have at least 11 vertices. Okay, so I'm just randomly growing a set and hoping that the cardinality stays good. Okay. All right. Okay, so now we just have to study the right-hand side. Okay, fine. Okay, so all right, here we start trying to do some math. Okay, so I want to argue that a sub I is bigger than I often, in particular, because I'm trying to avoid a sub I or the size of a sub I falling in that middle range. Okay, so I either want the algorithm to end very early, or I want the algorithm to go for a very long time and arrive at a giant component. Okay, so our first step then is just to generically analyze the expected value of a sub I. Okay. All right, so how might I proceed? Okay, how about this? Let's fix some other vertex u. What is the probability that u, let me simplify this more actually. Okay. Suppose I didn't worry about this part. I didn't worry about things terminating early. Okay. In retrospect, we'll show that a sub I is always bigger than I. So let's study the random process. This is now even simpler. So for each iteration, whatever AI is, I randomly sample from the remaining and I add it. I'm not even worrying about the terminating condition anymore. Okay. All right, so under this simplification, should have been there originally. Does anyone see a way to try to figure out the probability that a vertex appears in AI? Uh-huh. Okay, let's start small then. Yeah, so we know that the first layer, or before anything started, this is just one. So maybe as a warm-up, what is the expected number of vertices in A1? Okay, I guess 1 plus n minus 1 p, because each of those vertices have a probability p of being added. Good, good. If we can just figure out A2, I think we'll be almost done. All right, there'll be the one from the original vertex, fine. Is it what? Well, it's at most n, so I guess that's polynomial. Or I'm not sure which sense of the word you meant. I don't know what it is. Uh, oh, okay, okay. But then, well, that calculation directly assumes that A1 was actually n minus 1p, which is not exactly true. Okay, so yeah. Sure. Let's look at, okay, then if we can figure out for a particular vertex u, that's not V, because that's of course in A2. What is the probability that U is not in A2 for a generic U? Huh? Well, we could start smaller. What's the probability that U is not in A1? All right, 1 minus P. Good enough. What is the probability that U is not in A2? 1 minus P squared. So our process is now much simpler. Every round that U hasn't been sampled yet, we try again with probability P. We try again with probability P. We try again with probability P. So to not appear after 2 rounds, you have to get 2 tails. After 3 rounds, you have to get 3 tails. Tails happens with probability 1 minus P. Okay, so expected value of AI. I guess I'll write -1. I won't worry too much. 1 minus 1 minus P to the I. Okay, so those are the odds of getting tails all the time. And then 1 minus that. Okay. All right, so how do I deal with this? In particular, I want to upper bound this. Say this is less than equal to something, because then now let me show that the expectation is greater than equal to in our original calculation. Okay. What should I do here? This class only has 2 tricks. Yeah. Okay. E to the minus pi. Okay. All right. Fine. Oh, here's the. Okay. All right. So this trick has 2 tricks. So this is the easier one. 1 plus x is less than equal to e to the x. Okay. And then you have another one, which is it's less than equal to 1 plus x squared. Well, you could do x squared, that's fine. But this only holds for x, say, less than equal to 1. I think it's like x less than equal to a bigger number, but definitely for things less than equal to 1. Okay. And of course, because you guys kind of know that e to the x is equal to 1 plus x squared over 2 plus x cubed over 3 factorial plus x4 over 4 factorial, and all that stuff, right? This is Taylor series. And so what's going on is that for small values of x, sort of these lower order terms are dominated by the smaller terms, right? So if x is small, x squared, x cubed, x fourth, x fifth become more and more insignificant. Plus you have that factorial that's really driving things down. Okay. So for x small, e to the x is very close to 1 plus x, and very close to 1 plus x squared over 2, and very close to 1 plus. Okay. So we're going to apply that here. 1 minus I times p plus I times p squared. Okay. Now I'm assuming. Okay. Let me first write out the next step. I'm running out of space. It's getting complicated. Okay, so let me write this out and then I'll justify it in a moment. 1 minus ip plus epsilon times ip over 2. Why? Because I times p, so p was at most 1 plus epsilon over n. And I'm only worried about i's that are not extremely big, at most epsilon times n over 4. Okay, so that's all. So this thing is 1 minus epsilon over 4 times IP. Okay, some kind of small calculation. All right. Plugging back into here, and I hope I have enough space. So this is now at least n minus 1 times, what do we write? 1 minus epsilon over 4 times IP, or something like that. Okay. And what we already showed that IP is, this is 1 plus epsilon over 4. Epsilon times, whatever. Okay. 1 plus epsilon times I. It's not, I guess, too important exactly how I did the calculations, but ultimately we show that the expected value is at least 1 plus epsilon I. I suppose that maybe that's not too surprising. You know, the first iteration, you're hoping to get 1 plus epsilon on average, because the average degree is 1 plus epsilon, and so forth. Okay, so, fine. So we've shown that the expected size of A sub I is bigger than I by a fixed multiplicative factor, 1 plus epsilon times I. It was sort of gritty, it wasn't very pretty, but it can be shown. Here now then is the more interesting part. The claim is that the probability that the size of AI is actually smaller than I is at most epsilon squared I over 8. But the point is something exponentially small in I. Okay. All right, guys. Why? Chernoff bound. So what's kind of going on here then? Yeah, how are you applying the Chernoff bound? Okay, so this I here is pretty close to, not exactly the same, but it's roughly 1 minus epsilon times the expected value of AI, right? So the expected value of AI was 1 plus epsilon, was 5% bigger than I, and so this is roughly 5% lower than the expected size of AI. Okay, so this is really saying, what are the odds that AI is an epsilon fraction smaller than its average? Okay, good. Now our Chernoff bound as presented was a sum of xi's that were independent, right? We only get concentration in that case. So now what are the xi's that I'm summing up? Okay, so one could be like x1 is how many vertices I added the first round, x2 is the number of vertices I added the second round, x3 number of vertices third round. Now, that actually doesn't quite fit the format, but why? What could go wrong? Certainly they're independent, and they're non-negative, and we're summing them up. Yeah, so what could go wrong with that? So what if you get 2 in the first round? Oh, so you're defining a new one? Okay. So the alternate definition is, okay, so say x1, what would x1 be? Okay. Okay, so now probabilities are just indicators. So we can make and I suggest, I'm assuming this is what you had in mind. Um, so x10 will be 1 if the 10th vertex shows up in AI, otherwise it's equal to 0. Okay, so the sum of xi's will give us the size of AI. And these are all independent. If you look at our process that we're studying, right, each thing is being sampled was probably kind of independent of what happened with everyone else. Okay. So, okay, good. So that means that this uh, can be written as, what is the probability that x1 plus up to xn is less than equal to, it's really 1 over 1 plus epsilon times the expected value of the sum. Yeah? So the size of AI is equal to the sum of xi's. So if we sum up the xi's, it'll tell us how many vertices ended up in AI. Because each vertex that goes in AI gives us 1 point. Yeah, it's perfect. So that is mu. Okay. Of course, 1 over 1 plus epsilon is a little bit clunky to work with because we prefer something that looks like 1 minus epsilon. So, okay, we can conservatively say that this is at most like 1 minus epsilon over 2 times the expected value of AI. If you work it out, that's true. Okay. Now we can plug this thing in. E to the negative, our epsilon is now epsilon over 2 squared times mu, that's I, or that's at least I, over 2, okay, is equal to e to the negative epsilon squared I over 8. Okay. All right, so what have we shown? For any value of I, if I just ran this thing where it just keeps resampling, for any value of I that's at least smaller than epsilon n or something ginormous anyway, the odds of having I or fewer after I iterations is at most exponentially small in I. So in particular, for the large values of I, this is going to be really small. So, okay, so if, for example, I'm just looking at the values of I, that's some constant factor times log n over epsilon squared. I chose 32, okay? That I guess should be natural log, that's fine. What does that turn the right-hand side into? 1 over n to the fourth. Okay, so we just plugged in the 32 log n or whatever for i's. The epsilons canceled out. The 32 divided by 8 became 4. E to the log n became n. Negative side, put it upside down, or in the denominator. Okay, fine. So for values of I, they're much bigger than log n, or significant, bigger than log n. You'll never get AI less than equal to I at some level, or at least for any particular I. The odds are very low, like 1 over n to the fourth. Okay. All right, how can I take the last step and complete the proof of this gap theorem? So the claim is that there's no components of size like kind of between log n and something closer to n. Okay, so oops, I got this wrong. Okay, so 1 over n to the fourth gives us plenty to take the union bound over all values of I that are like at least 32 log n over epsilon squared. Okay, so what that tells me, I wrote this wrong, so it's a little distracting. So ultimately, the probability that AI is less than or equal to I for any I that's falling in this range. Okay, so for all values of I between something bigger than log n and closer to n, I will never have AI less than or equal to I. Okay. So now look at our algorithm. Either the algorithm terminates early, like before we get to 32 log n over epsilon squared, we just run out of vertices to explore. And then you have a small component. Or it's not going to fall in between and you get straight to epsilon n over 4. Okay? So if we imagine running the algorithm without the terminating condition as a thought experiment, with high probability you won't have any of the terminating condition for the middle range. Okay? So if the algorithm terminates, it has to terminate before it gets to 32 log n over epsilon squared, or after it gets to epsilon n over 4. Okay? So the connected component will have size either less than 32 log n over epsilon squared, or at least epsilon n over 4. Okay? So what's going on then? The reason why there's giant components or small components and nothing in between, because once you get big enough, concentration kicks in. So you might have been worrying about, having average degrees so close to 1 is so painful, right? And it seems like you're always on the verge of dying out in your search. But if you survive long enough, you've actually probably built up enough mass, so to speak, that you're kind of in the clear. Okay, so you see this sort of concentration of phenomena arising in funny ways. All right, does that part of the argument make sense? All right, let's see what we can do in the last 7 minutes. All right, so I'll go a little bit more quickly then.
This only proves that the probability of the size of the connected components in between is very small. It does not prove that the existence of the large component.
Yes, that's right. So that brings us to number 2, existence of a large component. Yeah, and then uniqueness is at the end. Yeah, so we just know there's no middle components. That's the hardest part of the proof, and yeah, the part where we get to use the Chernoff bound. Okay, so here's what we're going to prove now. Okay, now at some level, what we've shown is that if I'm doing my search from a vertex V, if I can just survive log n rounds, I win, because the next however many rounds are free. So I'm just trying to survive log n rounds. Okay, and this is saying that for any h, the probability of surviving h rounds is at least 1 over h. Okay, so in other words, for a single vertex, I have like a 1 in log n chance of getting out of the danger zone and getting to a giant component. Okay, that means any particular vertex probably is going to fail, right? But you have like n vertices at your disposal, right? Okay, so the first vertex, it was in a small component. Bummer. I'll throw out those vertices. I'm throwing out log n vertices. There's still roughly n vertices left, right? So there's plenty of vertices so that if this statement were true, one of those vertices will get you a giant component. Okay. All right, so how are we going to prove this? So this is a little bit more surprising. Anyone want to take a quick guess? You have 10 seconds. It looks a little bit like something we did last time. Yeah. Yeah, the process. Trust the process. Okay, so we had something similar last time. I looked at a binary tree, okay, where kind of there's 2 children, but each die was probability 1/2. Okay, and we said, oh, height 10 will get you probability 1 over 10. So we need a slightly more general version. So instead of doing 2, it could be some general factor k. Okay, so actually for us, there's going to be sort of closer to n children. Each was probability 1 over n. I could only draw 3. Okay, but in general, for a k-ary tree, so every vertex has k children, but then an edge only survives as probability 1 over k. So this isn't deleted. This should be survives. Okay, so most of the edges was probability at least 1 over k. So most of the edges get deleted, and you're only expecting an average of something close to 1. Okay, or deleted was probability 1 minus 1 over k. What was that? Yeah, that's okay. Then again, you get the same bound. The probability of surviving 10 generations is roughly 1 in 10. Okay, so it generalizes beyond factors, branching 2. You can do k for general k. Fine. The proof is similar, so I'm going to skip it. All right, so I want us to think of this process as how the population people think of it, instead of this sort of fixed tree and looking for paths in hindsight. Here's how the problem is often originally stated. You start with a population of size 1. Okay, so that's your first generation. Now to build your second generation, for each individual in the first generation, which is just 1 to begin with, is going to flip k coins, each of which flips heads is only probability 1 over k. So you expect 1 heads. Okay, and however many heads you get, that's how many are in the second generation. If the second generation has 2, then you're going to be flipping 2 over k coins. And however many heads becomes generation 3. Okay, so that's the same thing. Okay, the tree is sort of just in hindsight imagining all the edges there and then kind of deleting afterwards. Whereas this is sort of generating the edges in more of a forwards direction. Okay, but this is going to pattern match a little bit better for us. Okay, so, all right, so if we remember our search algorithm, imagine V being at the root and then sort of exploring the edges in breadth first search, or exploring vertices in breadth first search. So, okay, so I'm only trying to get to log n vertices or something, so H is pretty small here. As long as I haven't found H vertices yet, I can think of the next set of edges as sort of like taking that vertex Vi I'm exploring from and randomly sampling, n over 1 plus 1 epsilon or so children, each with probability 1 plus epsilon over n. So I can think of each step as sort of building out another part of the tree. Okay? So if the tree survives H generations or you reach AI equal H earlier, because maybe you fill up the earlier top parts of the tree like in a wide way, then you'll guarantee that AI is at least I, or all the small values of I. Okay, so we're able to map it to this tree. I'm only kind of giving a high level here because I knew we were going to run out of time, but that's okay. All right, so that addresses the existence of a large component. Any single vertex has like a 1 in log n chance of showing up in a component of size log n, in which case it's automatically part of the large component. There's no middle values. All right, here's the last part. This part's kind of cool. All right, so you might point out that we've now shown there's no middle component and that there exists a large component, but we've yet to prove the uniqueness of a large component, which is the last part. Okay, and this is going to go quicker than you guys might expect. So here's how we're going to prove this. Okay, so we're originally studying something where I sample for n vertices all the edges. Okay, but what I want to do is I want to imagine sampling sort of 2 halves. So here's n over 2 vertices here, n over 2 vertices here, and add all the edges within those. Okay. All right, so this is going to have some edges, and then afterwards I'm going to add the cross edges, and that'll give me a random graph of size n. But I imagine doing the 2 halves separately first, right? Okay, so what do I know about the red graph based on what we've already done? The red graph is going to have large components, maybe more than one. Okay. And for us, a large component is size roughly epsilon n, or epsilon n over 2 if it's half the graph. Okay. How many large components can the red graph have at most? 1 over epsilon or so. Okay, so there's maybe at most 1 over epsilon large components. And at least one. And that applies to the other side. So with high probability, this will have at least one large component, and not too many. At most 1 over epsilon. Okay. Now afterwards, I add the cross edges in this version of the experiment. Okay. So if I just look at one pair of large components, what is the probability I add at least one edge between them? Well, okay, so how many possible edges are there between them? It's going to be like epsilon squared times n squared over 4 or something. Or maybe I'm missing some constants. Fine, but roughly epsilon squared times n squared. N squared is a significant part. And each of those edges is showing up with probability p, right? And p is only like, it's like 1 plus epsilon over n. Okay, so the expected number of edges is looking like epsilon squared n. Okay, because p is close to 1 over n. Okay, so in fact, you're expecting tons of edges between any two of the large components in separate graphs. Okay, so what does that mean? Why does that tell us there's going to be a unique large component overall? That's the last sentence of the lecture. Why? Okay, so this is all going to get connected. We'll get all the cross edges across all the cross components, so all the large components get glued together. Okay, so then what's left is just one giant component. Okay, so that's it. So we didn't have time to prove the multiplicative turnoff bound. That's fine. This was just about, what would seem to be a simple concentration phenomenon about sums, which maybe you already knew because you knew what the normal distribution looked like, manifests itself to sort of have a similar concentration phenomena in more complex combinatorial structures. All right, thank you.